Let's start chapter 22 problems. I already started this one, this first one here. It's asking about units. Which one is it equivalent to? So the first thing we need to do is figure out what each unit stands for. T is for Teslas, and that's the unit of magnetic field, so I put B. Meter squared is area, A. Seconds is a time, so divided by time. So the best way in this case to find out what unit that's equivalent to is to know in which equation you find BA divided by time. And those variables come in Faraday's law. The induced EMF is the change in magnetic flux per time, because that flux was defined as BA cosine theta. So cosine theta does not have any units, and the number of turns does not have any units. So this quantity that has BA over time, so it has the right units, and since this EMF stands for the induced EMF, induced voltage, that's measured in volts. So that's how you know that these units are equivalent to volts. It's a little bit harder problem than most of the unit ones, but it just really wants you to be able to find which equation is relevant and be able to plug in the units for every single variable in that equation. For number 2, this is a Lenz's law problem because we're trying to find the direction of the induced current in a loop when a magnet is entering it. So the first thing we need to know is that when we have a magnet, that the magnetic field goes away from the North Pole and towards the South Pole. In this case, the North Pole is entering first. So if we have our loop over here, then we have the field going down into the loop and the magnetic flux is increasing. But you gotta really read the question. It says, as the South Pole leaves the loop of the wire. So it's not asking about what happens when it enters. So really pay attention to what it says. So what this one is saying, okay, now this magnet that had the north down and the south up, that has the magnetic field pointing toward that South Pole, this magnet is leaving the loop. So the loop is over here. This magnet is going down. So now let's figure out which way is going to be the induced current in this loop here. So the steps is, first step is which way is the field going? The field is going down. What is happening to the change in flux? Is it increasing or decreasing? So the magnet is moving away from the loop, so the field is getting weaker, so the flux is decreasing. So the last step is, if the flux was decreasing, then the induced current is going to want to produce a field in the same direction. Induced current will want to produce a field downward. So if you're looking at this loop from over here, from above, your eye is over here, and if you imagine a clockwise current going in this loop here, then use that right hand rule. Your fingers are curling. It's hard to draw this, but your fingers are curling like this, and your thumb is down. Your fingers are curling in here. Kind of bad picture. But you're curling those fingers in the direction of that current, making that clockwise loop, and that thumb is pointing down. So that's what you want. You want your fingers, trying this one more time, I just really didn't like that picture. You want those fingers to be clockwise, and that produces a downward field, which is what we want. So that's why, looking from above, these fingers are making a clockwise loop. Let's do number 3. So this one is talking about a wire or a rod, I called it a wire and a rod here, that is oriented east to west. It's in a magnetic field pointing north, and which end of the rod is positively charged, and the wire is moving downward. So what you have to do here is really figure out, okay, which way is east, west, which way is north, which way is down. So to visualize this is east and this is west, but I would not say that up is north, because up and north are two different directions, right? If you want the north, you don't point up to the sky. North is not up in the sky, south is not down into the ground. So if you visualize north as being this way into the page, north is this way and south is this way, then you can say, okay, up is up, down is down. But most people think that north is up. So if you have this visualized, then this becomes more clear here, that the wire is east and west, the field is pointing north, so according to our picture, that means the field is going into the page everywhere here. And the wire is moving downward, so down is down, so this V is down. So which end of the rod is positively charged? Well, use the right hand rule that says that you put your fingers in the direction of V, so we're going to put our fingers down, and then we fold them into the direction of the magnetic field. So that means our palm is facing the paper because we have to fold our fingers into the paper. So now we're folding our fingers. I don't know how I'm going to draw that, but with our thumb being here, when we're folding our fingers this way into the page, our thumb still points to the right. So the thumb is the force, right? V was the fingers and we folded. It's hard to draw our fingers folding into the page. So that means that the positive charges are experiencing a force to the right, because this right hand rule is for positive charges. So the positive charges end up over here, the negative charges experience a force to the left. So according to our diagram, that means that the east end is positively charged. And on a test, I'm not going to try to confuse you with all these directions, but the point of this problem is really to be able to visualize which way everything is going and how to use the right hand rule.